They're like, get it to go. Of course, we're still there's like 10, 15. Yeah.
All right. If you would turn in your books to page 349. 349, please. $349. All right, Jake, you ready to go here?
I'm just working on turnitin.com.
Oh, okay.
I'm ready to start.
Thank you. All right. Let's, on page 349 is section 5.6 that we're going to go on to today. Section 5.5, we're going to be skipping that one. That's just a little section on looking up antiderivatives in a table of antiderivatives. Now, that's kind of an old-fashioned way of doing things before we had these nifty calculators like we have here. Much like, if you went and talked to Mrs. Larson, she'd probably ask her if she has a CRC handbook or if she's ever heard of a CRC handbook. She would probably have a copy of one of those, and it's a big, thick book just full of chemistry formulas, physics formulas. I mean, there are variations of those handbooks based on what class or what thing you need them for. But it's a resource that scientists and whatever would use to find formulas that they may need. And a lot of times, we had one in the math office, I'm not sure it's still in there, a big, thick book like this, just full of different formulas. And when it comes to antiderivative formulas, most of you, your books have been recovered, so you probably don't have this. But if you've got one of these with the original cover on it, if you go inside the back cover, there is what it calls table of integrals. And there's like 64 of them. Okay? And they have a whole variety of forms, and they're kind of grouped by different forms. And, you know, if you had a certain integral that you couldn't do by U substitution or didn't work with integration by parts or whatever, you would look it up in one of these tables. And there's formulas for those. Now, there's 64 of these. In the CRC handbook that we had in the math office, there was a section just on table of integrals. There were 780 of them, I believe. And that wouldn't even be a complete list there. But these calculators are essentially, you know, an electronic table of integrals. I mean, they're all in there. Or the vast majority are in there. So if I type in a certain antiderivative, this will usually find it. And it may do it by some process of antiderivative that's programmed in, or it may just be literally programmed in. If one looks like this, with these numbers in these spots, you know, it just spits that out. And that's all programmed into it. So we have that, so we don't need to go physically look it up. It's kind of like when I was in middle school and we talked about square roots. And before, you know, at that time, calculators weren't too readily available, and the ones that were four-function calculators, and they didn't usually have square root and stuff on them. And we had a square root table in the back of the book. In the back of every math book had a square root table, and when you got into Algebra 2, it would have a log table. You could look up logs. When you got to trig class, it had a sine, cosine, tangent table. If you wanted to know the sine of 38 degrees, you looked up 38 degrees and read across to the sine column and went down, and there was your decimal. I mean, so we used those tables a lot. Before the calculators came along. So that's what Section 5 is. So we're not going to bother with that right now. It's really not something you need for the AP test or anything. How did I just get to that page? There we go. So we're going to go on to section 5.6. Now, we're going to think about again where we've been here in chapter 5. We started off with this idea of area under a curve, okay? Definite integral. We defined the definite integral. And you didn't even know where this S-shaped thing came from. We just said this means integral from A to B. It means the area between there and the x-axis. And we just, you just trust me, that's what it is. And then we just start talking about how can we find these areas. Well, the first way we can find areas is geometry. If your graph looks like a triangle or trapezoid or half circle or whatever, we can find that area. Unfortunately, that's very limited. Then, of course, we went on about a 2-week period where we went through the fundamental theorem of calculus and, oh, wow, look at this, the antiderivative, isn't this great? How it connects, an area, how could it be? And I got excited, and you did too. And so we, there we go. And we found out, wow, this is the antiderivative will let us do that. And we came up with fundamental theorem part 2, which says really all you need to find the area under even a non-geometric shape is just do the antiderivative. Plug in a B, plug in an A, subtract them, there's your area. Almost like magic, really cool. Unfortunately, what's the limiting factor there? Not all functions have an antiderivative, even though that book has 780 different formulas for antiderivatives, so not every function is going to have an antiderivative. So even though fundamental theorem part 2 is really useful for finding definite integrals, it will not work all the time. I could write up a very, very simple example here. Over here. The integral from 0 to pi sine of x squared dx. That's just, we could graph that. It's not a real hard graph to draw. It clearly has an area. But unfortunately, those first two aren't going to work for that. There is no antiderivative. So the only other option we have is some approximation to approximate that area. Now, we've done that with counting squares a little bit and stuff, but what we want to do is get much more specific about it. And along the way of getting more specific about approximation, we're going to be able to actually define what an integral is. We haven't really done that yet. We've just said, hey, it's the area. Okay, but it's going to be more than that. And so we're going to over the next couple days we're going to actually build that definition of what it is. All right, so on those little things that I sent you on your calculator, let's take a look at those. Go ahead and pull up the first one. Go into your documents, and in the AP Calc folder, there should be one called LRAM, RRAM, MRAM. Okay? Now, if you go up here and hit Control right arrow and scroll across through these pages you don't really need, you get to page 1.6. Now, in page 1.6, we have a function here, x squared plus 1, so it's just a little parabola, shifted up 1. We want to do the area from 1 to 3. Okay? Now, clearly, geometry won't work there. Now, this is one, we happen to pick one where we could do a fundamental theorem here. We could get the exact area with the function x squared plus 1. That'd be easy. But a lot of times we start with some simple functions that we could get the exact answer, and then we do an approximation anyway just to kind of compare. Okay, so we start with some easy ones. So one way to approximate would be to say, well, let's do some areas we know how to do. We know how to do rectangles. Let's put some rectangles under there. Now, is that a very good approximation? No. But the name LRAM, RRAM, and MRAM, what LRAM means is a left rectangle approximation method. Left rectangle approximation method. Why are these called left rectangles? The left endpoint is on the function. The left endpoint of each of these rectangles, or each of these, what we're going to call subintervals. A lot of terminology today, okay? The integral goes from 1 to 3. That's the interval that we're looking at, from 1 to 3. We're going to break that down into subintervals. In this case, 4 subintervals. Okay? And so that's going to be an L4. We're going to call that an L4 approximation, as you'll see the notation here in a little bit. Now clearly that's what kind of an approximation? Very poor, not very good. With 4 rectangles with a curve like that, it's not going to be very good. And how's it compare to the true area? It's less. You're going to hear terms like under approximation. We'll use that term a lot, an under approximation. Okay? But the key is, but you think about, well, how will you calculate these areas? Well, the width will be easy. The width of the rectangle is easy. If I've got a total width of 2, 1 to 3, got a total width from 1 to 3, gives me a width of 2, and if I'm going to do 4 equal width rectangles, 2 divided by 4, each one of those has to be a half wide. So the width is easy to find. And what's the height? The function value, the output. And so even if we had a function where we couldn't do the antiderivative, we could still take these values and plug them into the function and get outputs. And so that'll give us our function heights, our rectangle heights. So the function values are the rectangle heights. So we're going to have height, we're going to have width, we can get the area. No problem. Now, go to the next page, and this one shows a right rectangle approximation. Clearly, the right endpoints of each subinterval are on the function. So the right rectangles determine the heights. Now, this is an over estimate, an over approximation of the actual area. Let's go to the next page. These are midpoint rectangle approximations. Okay? In each subinterval, we go halfway into the interval and plug that number into the function to get our output, to get our height. And then we draw a rectangle this way. Now, you're going to be doing some drawing. You'll become artists today. You will be doing some drawing on our next quiz next week, probably be next Thursday. You will have some problems where I'll say, draw 4 right rectangles for this picture. Draw 8 left rectangles, whatever. Okay? And so you're going to need to draw the function, divide up your interval, draw the rectangles in there. Okay? Now, this one looks pretty good, right? I mean, this one, you know, you can see these different approximations. This one is 10.6. I don't think it says the exact area here, but that one's probably relatively close. Okay, now, oh, by the way, there's nothing magical about left, right, and midpoint, though, for getting our function heights. I could have picked any point in here. Your book's going to call it a sampling point. I could have picked any point in this subinterval, plugged it into the function, and used that as my height. Okay? It doesn't have to be at the left end or the right end or the midpoint. Those are the ones we usually use. Okay, get that other document. Go into your documents and get the other one I sent you, which is called Riemann sums. Open that one up. Now, the neat thing about these for you to have on your calculator is you can go in there and you can grab some of those points and you can drag them so you can resize the graph and see some things. This one's actually kind of cool. So if you open that one up and you scroll over here to page 3, this gives you kind of everything all on one page. Okay? We can see this now. This time we got x squared plus 2. Here's our 4 left rectangles. We can come up here and we can grant it tells us our approximation. Clearly we're under approximating the area by quite a bit. But go up here and grab the little slider and drag it to the right. Watch what happens. Okay, here's my. Is it pretty slow or does it work pretty good?
Pretty good.
It works pretty good. I mean, sometimes the graphics kind of slows down. Okay, now think about this now. I've got 29 rectangles, right? 70 rectangles, whatever, 75 rectangles. Now compare that to something we've already done this year. Well, no, because we did do a little bit of area. But I mean, we don't know how to find the area under this curve. It's not geometry. Yeah, I mean, basically we have an area we can't find, We don't know how to do the area under this curve because it's not geometry. So we say, let's do something we do know how to do, which is the area of a rectangle. And then let's put rectangles under there, but they're not really exact. But let's do more and more and more rectangles. And the more rectangles we do, the closer and closer our answer is getting. What's that compared to? Slope, right? We said we want to do the slope at 1 point. We don't know how to do the slope at 1 point, but we do know how to do the slope at 2 points. So let's do the slope at 2 points, and now that's an estimate of the slope at the 1 point. Not a real good estimate, but if we let the 2 points get closer and closer and closer, right? Same thing. Same exact thing. Okay? That's the approach we're going to take. So our definition of an integral, our definition of area is going to come from this. It's going to involve a limit. You're right. It's going to have the limit. Remember the definition of derivative? Limit is h approaches 0, right? Let the 2 points become 1. Here we're going to basically say let your rectangles go to infinity to get the true area. If you could do more and more and more rectangles, eventually you get closer and closer to where you need to be. Okay, so that's kind of where we're headed with this, but we got to work through all the notation and all those things before we're ready to do that. Okay, so here's what, and then the other cool thing you can do with this is you can drag this little dot right here where the L is, and you can drag that over and you can look at midpoint rectangles, and you can look at right rectangles, right? And you can look at, and then trapezoids. Here's the other one. Now this is another, now this was kind of on its own. We're going to talk about rectangle approximations. Now trapezoid's not a rectangle, obviously, but it's pretty good. It does a pretty good job. Okay? Now, do you see why those are trapezoids? Two parallel sides, the up and down here. You just do the left end of the subinterval, the right end of the subinterval, and you connect them. You just connect with a straight line. Now notice your answer is a little bit of an over approximation. Why is it a little bit over? Because the red curves up, but the blue line on the trapezoid is straight. There's going to be a little gap there, and you can't really see it very well. There's a little gap. Maybe if we went with a few less trapezoids. Can we go down to, yeah, 1. There you can see it. 2, 3, you can see it a little better. Okay? But, you know, but the more and more you do, the better and better you get. So you might think, well, why would you ever do anything but trapezoids and mid? Why would you even do lefts? Right? Left rectangles or right rectangles are pretty bad compared to trapezoids. Trapezoids do a much better job. Well, the thing is, you're right, for 4, if we're going to do 4 of something, yeah, trapezoids will give us a better answer. If we're going to do 8 trapezoids will be better than 8 rectangles. But we're talking about going to infinity, right? If we do an infinite number of something, it doesn't matter what we do. Right? Left rectangles, right rectangles, they're all going to eventually give us a good enough approximation. Okay, so anyway. So that's what we're talking about going into. Okay, some of this you're going to have to do by hand. That's what we're going to focus on over the next day or two. Then eventually we'll be able to use our calculators to do some stuff just to automatically do it. Now the cutoff for us is going to be double digits. If I ask you to do 8 left rectangles, you're going to write them out by hand. If I ask you to do 10 left rectangles, you're going to have a program, you're going to have something on your calculator where you can just do it. So 10 or more, you'll just do it right on your calculator, give an answer. Under 10, we're going to be writing them out by hand. Okay, and we're going to start with that. We're going to start with doing it by hand because we need to go through, just like when you're in grade school and you learn your times tables, you learn the process of adding and log division, you learn a number sense you gain from that helps you as you go on to the things, and that's the same thing we're going to do. So it's not just busy work that we're doing by hand. It is going to lead to something that we'll be doing first part of next week. So you just have to trust me on that. Okay, so I want to look in your book here. Oh wait, there is one more thing I wanted to show you here real quick. I've got a little more complicated function we can look at. Here's a function that kind of goes up and goes down a little bit, and we're looking for this area. And so if I had left rectangles, notice some are above and some are below. Now that brings up another couple terms that you sometimes hear. We won't use them very often in here, but they show up in the packets. Inscribed rectangles. What would inscribed rectangles be? Inside, or in this case, under. So in that picture we had up there a minute ago, left rectangles, these would be inscribed rectangles. They're left rectangles, but they're also inscribed rectangles. The right rectangles here would be right rectangles, clearly, but they're also circumscribed rectangles, which means outside. Okay, so sometimes you hear the term inscribed or circumscribed. Now, if you go to this one, they're left rectangles, but they're not either one of those other two. If they ask you for a problem where they wanted inscribed rectangles, every rectangle would have to be under the curve. So you might have a left rectangle, then the next one might be a right rectangle, then the next one might be a somewhere in between rectangle, right? You'd have to find a point in that subinterval. You'd have to find the lowest point in that subinterval, and that would be your rectangle height, because you'd want all your rectangles to be under or over, depending on what they ask for. Okay? We don't run into those very often, but that's what that means. All right, so here's 3 left rectangles. If we keep going, there's 4, 5, 6, right? We keep getting more and more. We can go up by tens, right? And clearly we can see we get a lot of rectangles. Okay. Okay, stop going. There we go. All right, so those are lefts. Here would be rights. Those are both over, but if you keep doing more and more, some are over, some are under. Okay. Here would be some midpoints. Okay. Let's get these off here. Okay, there's 4 midpoint. Now notice they draw this black line in here, which is the midpoint of this subinterval. That's the height, and then you draw left and right. Here's the midpoint here. Here's the midpoint here. Here's the midpoint here. Okay? You're going to have to be able to draw some of those by hand, and we're going to go through and do those. Okay, so all right. So number 17 in your book. You're going to have one in your homework just like this. Now the homework isn't very many problems, but they do take some time because we got a lot of stuff to write down. So we're going to get through this. I'm trying to hopefully give you some time to work here. You're going to have a problem just like this. This one problem will take most of your homework time probably. So we're gonna do one like it here. All right. All right. So we have the integral from -2 to 2 of x cubed dx. Now the directions say, and this is on page 355, it says to draw a sketch that illustrates, or it's actually sketches, we're going to do 4 sketches, that illustrate L4, R4, M4, and T4. Then we're going to compute each approximation, and we're going to compare those with the exact value that we get using the fundamental theorem. So let's do that first. So the fundamental theorem would get what? 1/4 x to the 4th from -2 to 2. So we put in a 2, we get 1/4 times 16 minus 1/4 times 16 equals 0. Well, then we start thinking about it. Think about the x cubed graph from -2 to 2. Odd function, symmetrical, you got some below, some above, they're going to cancel out. We should get 0. Okay, so that is the exact value. Of course, if that's all we cared about, we would never do an approximation on this one because we're just interested in this. Now, keep in mind that I realize when we do 4 rectangles, it's not going to be a very good approximation. I understand that. Okay? What we're trying to gain here is an understanding of the process of that. So we can get the definition. Remember, when we learned our derivative formulas, they all came from the definition of the derivative, which was f of x plus h minus f of x all over h, right? We had to get a sense of 2 points becoming 1 point. That's what we're trying to do here. All right, so here's the first one we're going to do, L4. That's how we write it, L4. That means a 4 left rectangle approximation. The way we write these is what's important. because of some stuff that's going to happen over the next 3 days. All right? We're going to be looking for patterns. And so how we write them is going to help us to see these patterns. So before I write it out, I'm going to draw a picture. So here's my x cubed. Here's negative 2, negative 1, 1, and 2. Okay? So, now, I jumped ahead of myself here. What's probably the first thing before we draw 4 left rectangles that we need to know? How wide they're going to be, right? I need to decide how wide they're going to be. How am I going to determine how wide they're going to be? Okay? The formula is b minus a divided by n. Now, that doesn't seem like something we would have to really memorize or anything, but you'll see why we'll be using it more later on. Here's some more terminology. Delta x stands for change in x. That's going to be what we will use to denote our width. Delta x for us is going to mean the width of our rectangles. Okay? It's a change in x. Well, for us, that's, you take your total width, which in this case is 2 minus negative 2, but wouldn't that always be b minus a, right? B minus a would be your total width. They're going to divide that by n, which is your number of subdivisions, your number of subintervals, your number of rectangles. Well, clearly this is 4 divided by 4, which is 1. So this will be an easy one. We're going to have a width of 1. That's nice. So I went ahead and divided that down into increments of 1. All right. So my first left rectangle, how will I draw that? I'll start at negative 2. I'll go down to the function. And then I'll go over to the right 1. And then back to the x-axis. And shade that in. And there is a left rectangle. Just like the pictures we saw earlier. You can always go back to your calculator and look at those to help you. But the left end, and again, we call those the subintervals. Our interval is negative 2 to 2. These are the subintervals. Okay, the next left end point is right there at negative 1. We draw a cross, 1 wide, and we've got another rectangle. What about our next rectangle? There won't be one, right? The left endpoint has a function value of 0. That's the height of your rectangle. Now, you might just draw a little squiggly line through there or something just to show that you got something going on there. But there is no left rectangle. It has an area, a height of 0. And then the last one at 1. Now, again, this is clearly a terrible approximation, but it's going to be. Whenever you have just a very small number, it'd be like doing a slope calculation where you had 2 points that weren't even very close to the 1 point you were looking for. I mean, it's not going to be a very good approximation. Okay? But that's not the point. I mean, that's not what we're trying to gain from this. All right, now, here's what I want you to write for your estimation, for your approximation. We're supposed to calculate the L4 approximation. Here's how I want you to write it. Our first rectangle has a height of f of negative 2 times a width of 1. And you're saying, why do we write the 1? I understand that. We're writing it, okay? I want you, when you look at these, I want this to look like a sum of rectangle areas. So I want to see a height times a width. All right, what's my next height? F of negative 1 times 1 plus f of 0 times 1 plus f of 1 times 1 equals, and here's where you'd be able to get your calculators out. Matter of fact, now this is an easy one. This is an easy one because the function's so easy. But one of the things you'll probably start to get in the habit of is on your calculator in the scratch pad is just define a function, like define f of x to be whatever this is, because sometimes this is a complicated function. We're going to want to plug a negative 2 in, plug a negative 1 in, plug a 0, plug a 1 in, right? Well, if you, on your home screen or on your calculator screen, if you just define f of x to equal x cubed, then you can just type this in just like this. You just type it in, f of -2 times 1, blah, 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 and it'll just do it. It's kind of a nice way to shorten it a little bit. Anyway, this is pretty easy. We get -8. -1 cubed is -1. 0 is 0. 1 is 1. For a total of -8. Right? And you can tell by our picture we clearly have much more negative area than positive area. And again, it's a horrible approximation of our answer here, but that's not the point. The point of it is we look at this F notation, we kind of see, oh yeah, when -2, -1, 0, start at the left endpoint, moved over one width at a time. Those are all the kind of things we're wanting to see as we do these, okay, that are going to become important to us. But for now, we just get in the habit of the process and writing this down. Okay, let's do an R4. Okay, we got 4 of them we got to do here. So we redraw our function. Okay, what's going to change on our picture this time? So where's my first right rectangle? How am I going to draw it? You're going to start at -1, aren't you? You're going to go to the curve there, and you're going to go backwards to the left, like so, right? Because you want the first subinterval, you want to use its right endpoint as your function height. And then the next subinterval, the right endpoint is the 0. So that's the one where we don't have any rectangle height. The next one is at 1. The next one is at 2. Okay? And so we end up with 4 right rectangles. And what about your R4 expansion? I'll call this an expansion where we expand it, we write out all 4 rectangles. F of -1 times 1 plus f of 0 times 1 plus f of 1 times 1 plus f of 2 times 1. And as we do all that, we have most of those values. That's -1 plus 0 plus 1 plus 8. So this time the answer comes out 8. Which, because of symmetry and so forth, we see that this is kind of an average. If we average those two, we get the exact answer. But that doesn't always work. Just because the lefts are under and the rights are over doesn't mean you average them, you get an exact answer, right? I mean, because one might be over because, again, it's curving, so that may not happen. Okay, we got 2 more to do. M4. Okay, again, these get more complicated if the width is 1/4, you know, or 2/5 or something like that. And then, you know, and then the writing out of it is especially important to keep track of those kind of things. Okay, now how about this one? What are we going to do here? Those middle points, right? Now, and so even this one gets a little, I usually come in here and make these marks a little bigger, and then just put little marks in for the midpoints, right? So I don't confuse which are my subintervals. The big marks, those are my 4 subintervals. And then in this midpoint, I'm going to come down to the function, and then I have to draw back to the left and a little bit to the right, right? Half a width each way to get my rectangle. And then on, just get little tiny rectangles here on these okay. Now that one actually looks like it's going to be 0, right? Looks like that's actually going to be exact. And again, that the symmetry of x cubed is what makes this happen. That doesn't usually happen. Now, how do we write this one? Well, we're going to be looking for patterns, so decimals are okay. Fractions sometimes are better. It's up to you. You can use decimals if you want. You can use fractions. But what's that first function that or value that I plug in? negative 1.5 or negative 3/2. I'm going to go ahead and use fractions here, but decimals would be fine. Negative 3/2. The next one is a negative 1/2. Next one is at positive 1/2. And then the last one is at 3/2. And again, they still all have a width of 1. They all still have a width of 1. And I believe if you type that into your calculator, if you actually do those calculations, they'll come out to be 0 because they'll just be opposites of each other. All right, last one here for this problem. Draw T4 for trapezoids. Again, the width is still one. Now, how do we draw a trapezoid?
You would do from like -2 and 1 down through the curve and then just connect those.
You just connect the dots. Now, sometimes you have to overemphasize it a little bit because of the curvature. In this case, it's concave down the way it's curving. So the line would actually, the line of the trapezoid will actually be below, right, the curved part of it. That's how you draw a trapezoid there. Okay, what about the next trapezoid? It's actually a triangle. Okay, now, that's okay. Right? Think about the area formula of a trapezoid. 1/2 B1 plus B2 times the height, and B1 and B2 are the two parallel sides that are going up and down here. What happens if one of them's 0? 1/2 base times height. It's a triangle, right? So that's not that big a deal. If one of them's 0. As a matter of fact, in your homework, you're going to have a thing where one of the endpoints, you're going to have a curve that goes like this, and so the one endpoint is here, and the second endpoint is there, and there's your trapezoid. It actually goes from below to above. Well, what you do is you get two triangles. Well, that makes sense. If you think about this, if you took 1/2 height and distributed that through, right? Isn't that really just two triangles, right? If you do 1/2 h and distribute it, you get 1/2 B1 height plus 1/2 B2 height. That's really two triangles. So the nice thing about it is, when we go to write this down, we're not going to have to worry about that. We're not even going to have to worry about, oh, it's a triangle, oh, it's two triangles, oh, it's a trapezoid. The trapezoid formula handles all those situations, so we'll just use the trapezoid formula. Okay, so anyway, here's this one is another triangle, and then here we actually get a trapezoid on the last one. Okay, so this one's a little longer to write out because it is this trapezoid formula. So it's 1/2. Now what's B1? What's my first base on my first trapezoid? F of -2 plus F of -1, and then times my width of 1. Right? Plus 1/2 parentheses F of -1 plus F of 0 times 1. Right? I mean, this is what our trapezoid formulas look like because the function values are those bases, those parallel bases. Plus 1/2 F of 0 plus F of 1 times 1, and then plus 1/2 F of 1 plus F of 2 times 1. And I think as you look at that, because of the symmetry, again, we get 0. But normally we would have some calculating to do there to get those values. Now, one of the things you notice about trapezoid, we're trying to see some patterns here. You notice that you use all of them all the way from -2 to 2. On this one, you started with -2, but you went to 1 on the left. On the right, you went all the way to 2, but you didn't use the one at the far left, the -2. Here we use a -2 and the 2. And we use the other ones twice. We use a -1 twice, a 0 twice, a 1 twice. Those are some patterns we'll see that will allow us to develop some rules and some formulas and things like that. But for right now, we're going to write them out and get comfortable with that, and then making those patterns develop will be easy. Okay, rest your hands a minute. Okay. And turn back to page 352. Turn back to page 352. $352. Oh, was it? Well, we were on 355 for that problem. Or I had said something. Okay. Now. Yeah. Well, at least somebody around here is. All right.
In the math office? But she's kind of a strange place for it.
I don't think it's in the math. All right. Now, on this calculator document that we called Riemann sum, okay, the one I sent to you, or that was named Riemann sum. Okay, Riemann's the name of a guy that's named after, but a Riemann sum, just think R for Riemann, R for rectangle. Okay, a Riemann sum is a rectangle sum. All right, now, by definition, a rectangle sum is just adding up all these rectangle areas. Now, I said they could be left endpoint rectangles, right endpoint, midpoint, or any point in between. And here's another thing I didn't say, but it is true. The rectangles don't have to be equal width. We said over here that we'll let delta x be b minus a over n. That's if we have equal widths. 98% of the time we'll have equal widths. And we'll use left and right and midpoints. But it wouldn't have to be that way. I could do rectangles. Turn to page 351. Look at the bottom of page 351. That's a Riemann sum. It's got 6 rectangles. They're all different widths. They all hit the curve at different places. Some look like they're about the midpoint. A few of them look like they're right endpoints. And some of them look like they're just kind of in between there somewhere. That's a Riemann sum. Okay, so we're going to write down the definition of a Riemann sum. You're not going to have to quote this word for word, but it is something we need to understand. Now, when you hear Riemann sum, the kind of ordinary language, the common, the kind of the common ordinary language, you want to think of it as sum of rectangle areas. That's what it is a Riemann sum. The sum of rectangle areas. Okay? What? All right. Quotation. All right. So that's what you want to think of. But here it is in more formal language. Okay? First thing, I'm going to kind of paraphrase this a little bit. We're going to divide. We're going to divide the interval AB into n subintervals. Okay, we're going to divide AB into n subintervals. Now, the way we divide that, a couple little technicalities here. If we look at this problem we had over here on the board from -2 to 2, we divided that into 4 subintervals. Now, it took 5 points to do it. If you think about that, -2, -1, 0, 1, and 2. That's 5 different x coordinates on here that broke it into 4 subintervals. Okay? So we're going to divide this into n subintervals. We're going to need n plus 1 sampling points. And so since we'll need that, we're going to start with our first one being x sub 0, which will be less than x1, which will be less than x2, ... which will be less than x sub n minus 1, which will be less than x sub n. Now, x sub n is the b, that's the far end, and x sub 0 is the a, that's the left end. So the reason we start calling our first point x sub 0 is because we need one more than the number of subintervals we have. So if we have n subintervals, okay, so that's why the x sub 0 is there. So think of this here as x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4 in this example we have. Okay? All right. So we're going to divide into those intervals, and we've got two important pieces of information. One is our width, delta x. Now, I can't call the width delta x because it's not going to be equal all the time. So I'm going to call it, I'm going to have a delta x1 and a delta x2 and a delta x3 because each width could be different. So I'm going to call that delta x sub I. I is going to be the number of the subinterval. First subinterval, second subinterval. Here we had 4 of them. First subinterval, second subinterval, third subinterval, fourth subinterval. Okay, so I think you look on your book there, it talks about the ith subinterval. So delta x sub I is the width. Okay, that's good enough. That's the width. But understand they could be different. There could be delta x1, delta x2, delta x3, and so forth. All right. The height is going to be f of, oh wait, time out. Jumping ahead of myself. C sub I is any point in the subinterval. Okay, remember, now it could be the left endpoint, it could be the right endpoint, it could be the midpoint, or it could be any point in that subinterval. By subinterval, again, I mean between -2 and -1, or between -1 and 0, and so forth. And there's a little subscript I there because we got I of those subintervals. All right, so my sum then will equal the first rectangle area plus the second rectangle area plus the third rectangle area, plus the nth rectangle area. How would I write the first rectangle area? Well, I would need the first rectangle height. Use our work up here as an example. How would I write the first rectangle height? F of, what would I put in here? C. Right? C. Because what do we do here? Here we use the left endpoint of the first subinterval. Here we did the right endpoint of the first subinterval. Here we did the midpoint of the first subinterval. I said C sub I is any point in the subinterval. So whatever point we want, could be left, could be right, could be midpoint, that's what C sub I was. So I'm going to plug any point in the, now I'm sorry, back up. I don't want that to be an I want that to be a 1. This is our first subinterval. So f of C1 is my function height. What's my width? Delta x1. There's my first rectangle area right there. Second rectangle area is f of C2 times delta x2 plus ... And my last rectangle area will be f of C sub n times delta x sub n. Now I know that's just a lot of gobbledygook, but that is called a Riemann sum. Again, what is it? What is it? It's just what I said right here. It's the sum of rectangle areas. That's all this is. This is a sum of rectangle areas. First height times first width plus second height times second width. ... Last height times last width. Add them together. That's the sum of rectangle areas. Now, you might, why do we have that? We're getting to that. Next, tomorrow we'll get into that some more. That is the sum of the rectangle areas. Okay, the next problem we're going to do then is the first one in your homework. We're going to do that one together. I think that's what I want to do next. Yes. And then you'll have time to work, the rest of the time to work on your homework. So, on the assignment sheet, we get out our assignment sheet here. Go Go down to where it says 5-6, 5.6, I guess, section 5.6. Okay? Just the 5.6 line is all we're going to do. That's plenty. 25 and 28, don't spend much time thinking about. I told the other class I should just take them off the assignment, but a lot of times everybody will do the assignment except for the last couple, and you'll just leave those off anyway. So if I don't want you to do 25 and 28, I'll just say go ahead and do them, and then if you leave them off, it's no big deal. But if I take off 25 and 28, then you won't do 16. See, that's what I mean, then you won't do 16. And 16 you got to do, because 16 is like 17, and I'm going to see all that tomorrow. So got to do 16, no excuse, because you just saw 17. But so 25 and 28, don't worry about it. Don't worry about 25 and 28. We'll talk about them tomorrow. Okay? So we got 1 through 6, we got 7, we got 10, we got 16. I want those done for tomorrow. Now, 1 through 6, somebody asked why I didn't say 1 through 7. Well, 1 through 6 is a group of problems, and we're going to do number 1 together, and then you'll go through the other ones. It's involving some drawing. When I come around and look at your homework tomorrow, I'll be looking for pretty pictures, sketches. Okay? Yeah, you'll draw very specific pictures. All right? So if you turn to 355, 354 actually, you are going to, if you see that picture there on number 1, you are going to redraw that picture 6 times for the first 6 problems. Not for each problem, just, okay? You're going to have one drawing for 1, one drawing for 2, one drawing for 3, through the first 6. Now, number 16, you've got 4 drawings. Yeah, that's like number 17. All right, so let's do it. So, and make a fairly decent sketch, please. If you want to put your paper over your book and trace it, that's okay. But I'm going to go ahead and plot some of these points real quick. Looks like this. I believe. Okay, so it doesn't have to be perfect. I mean, but you can just, if you get the general shape of it, crossing the axis kind of in those positions, that'll be, that should work. And what they do in the first 6 problems is they ask you to do just what we did in number 17, is to draw a sketch and then write out an approximation. Okay? Now for number 1, they ask you to do the whole width, -5 to 5, and that graph is g of x. Okay, so this is the g graph here. And number 1, notice there's a part A and a part B. Well, part A is to estimate the sum, or to write out the sum, and part B is to draw it. Now, I'll be honest, I like to draw it first, and then do the estimate. So let's go ahead and do that. So we're supposed to draw 5 left rectangles. So our first job is what? Get the width. So 5 minus -5 divided by 5, which would be 10 divided by 5, which is 2. So our subintervals are going to be 2 wide. So I might come in here and put in my 6 marks. Remember we said you always takes 1 more. I might go in and you know, you wouldn't have to do that, but those are my 5 sub-intervals. They have to be 2 wide. Okay, and these are supposed to be left rectangles. So here we go. What's that? It was one of the pages, yeah, the one we did last period, you mean? I believe that's right. It's a little easier if you have graph paper or composition paper or something. But I've got some graph paper up here actually if you want it. But or I guess on the order. Now, so for the first 6 problems, you'll be drawing a picture for each of those first 6. You do a separate picture. Don't try to draw them all on one graph. That would just be a mess, and you wouldn't be able to tell anything. Now, the next thing we're going to do here, we're still not done with number 1, is we need to write out our estimate. Now, they say estimate, but you're not really going to estimate unless, of course, you have to read off the graph since they didn't give us an equation like we did in 17. They just gave us a graph. We may have to estimate our y values because they don't land on a specific spot. But otherwise, the only reason this is an estimate is because our area is not the exact area. We're estimating this integral. Okay? We're not estimating these rectangles. Again, unless the height doesn't fall right on a nice point. But the next thing we're going to do, so then we're going to write this out. So this is what I want to see. So we're doing an L5 here. And so we're going to start here with f of negative 5 times 2 plus f of negative 3 times 2. Does that make sense? I mean, because we got to go over 2, right? We start at negative 5 is our first function height. Our next function height is at negative 3. The next one's at negative 1. The next one's at 1. And the last one is at 3. And this, when we're doing fewer than 10, I want to see this written out. And using the F notation, I want to see that. Now, I wrote F. That was silly. Okay, I'll just change this function to F. Should have been G, okay, because this function was named G here in this problem. But okay, so it should have been G. All right. So negative 5. Now this part you can do. I mean, this part you don't have. The rest of it you don't have to write out. If it was a function like x cubed, you can define it on your calculator and plug that in. That'd be fine. You know, the rest of it you can do in your head if you want. But I want to see this part of it written out. So f of negative 5, of course, is negative 2, and f of negative 3 looks like is 2, and f of negative 1 is, 1, 2, 3, and f of 1 is 0, and f of 3 is negative 1. So we get negative 4 plus 6 plus 0 plus negative 2. So it looks like we get a final answer of 4. Right? So, on 1 through 6, it'll look like that. 7 and 10 is similar. They give you a graph and they say estimate, you know, do the L3 or whatever. You do not need a sketch on those. It does not say draw a sketch. So on 7 and 10, you don't need a sketch. You just need to do that last part we did, where you write it out. But you do need to write it out. Okay? And then on 16, you're going to mimic what we did on 17. All right. Rest of the time's yours to work. Yes. Yes. Didn't we do that yet?
No.
Kenzie? Why? Zach? Tori? Alex? Daniel? Matt? Chris? All right, now, if you want to come up and ask me individually about things you missed, that's fine. Remember, we need to get this done. You need to get this done by the end of the term, which is March 6th, 2 weeks from yesterday, which is plenty of time. You take one a day or one every other day. You should be able to get 4 or 5 for sure, and you should pass by then. If you're not getting them passed, you better be trying one every day, maybe. You better be studying up for it a little bit. Gateway. Now, if you don't, and obviously if you don't pass it or don't take them or whatever, by the end of the term, you just take whatever grade you have. What do you want? Number 7, probably your X is one that was that's extra. That should be one that she there. Oh, I always that should be -2. Okay, because you've got you put in pi hand, 3 pi hand, that'd be 1. Cosine pi hand is 0, so you get this. Minus, and then, here's one. Because you got UV